This is the first tutorial of a series of 3, and basically this tutorial is going to explain the fundamentals of going through the process of applying a neural network to a basic application, which is a quadratic function. This is a good place to start. So it shows the different steps. The second tutorial shows how to actually run the software, and the third tutorial shows running the software itself. So we'll start with just a description of the mechanics of a feed-forward neural network. Obviously, you can go to the internet and get much more detailed explanations, but we'll just touch on this before we begin. So this is the basic feed-forward neural network. You have an input and an output, and in between a series of neurons, as we call them, which are really simulated by a hyperbolic tangent function. So from each of these neurons, these hyperbolic tangent functions, comes a signal which is multiplied by a gain, and that's input to the next activation function or neuron. Each activation function processes all the signals coming in, each signal multiplied by a gain, and then that's processed through the hyperbolic tangent, and it outputs another signal, and the process continues, and it's multiplied by a gain, and the next neuron processes these signals as a hyperbolic tangent function, and so on. So we call each of these neurons, these are called, this is the input layer, output layer, these are called hidden layers. There's other names for them as well, but so this would be the first hidden layer, second hidden layer, and there's 2 neurons in each of these hidden layers. These gains are determined by a learning algorithm. There's backpropagation, which is very old, Levenberg-Marquardt optimization, which is what I use for all the applications that either I'm working on or the ones I've worked on in the past, but there's many other types as well. So the main thing is this is a neural network. You have, the thing you remember is you have an input, you have an output, and you want it to learn that given this X input to produce this Y output over a series of data points. And these can become much more complex, where you have several inputs and several outputs, and then much larger sets of neurons in the hidden layers and so on. But anyway, that's the basic description, and we'll move to the next slide. So we have a series of steps that we want to go through, and the sequence of events are as follows, and I'm just going to read these. You want to generate the data set from which you want the neural network to learn. In our case, we're going to use a quadratic function. So you have to generate the data. If you're going to do a flight control system, then you've got to get the flight control data whatever you want to train the neural network on, you've got to get that data. Then you're going to select values from the data set that you want to use for training and values that you want to use for testing, and this is extremely critical. This is probably one of the most important parts of getting a neural network to work successfully. I would say it's about 90%. Then you scale the training and test sets to fit within the domain of the neural network input and output regimes. This is a pretty basic step. Then you select and set the neural network architecture, which could be number of hidden layers, number of neurons per layer, etc. And then you train multiple neural networks, because some are going to perform better than others. Then finally you test each neural network with the test data and determine the neural network with the best performance. And that's basically it as far as the steps go. Okay, so now we're at step 1, and we want to generate the data domain set is what I call it. And in this case, we're going to use a quadratic function to generate a highly nonlinear curve, because we want to show the ability of the neural network to map nonlinear functions, regions, things like that. So in the end, what you're trying to do is to say that when a value of X is input into the neural network, it will produce the correct value of Y, or close to it. So for example, when you have your trained neural network, you can input a -10, which obviously has to be scaled, but let's say you put in -10, the neural network should output a value of 100. If you say +10, it should output a value of 100. If you put in a value of 5, then it should be approximately a value of 25 or 20, whatever that is, and so on. So this is just the first step. You want to generate your data. Okay, so this is the second step, where you want to select the training and test data points, and this is actually, you'll learn this if you really get engaged in the applications of neural networks to real projects, that this is the most important part of getting a neural network to work successfully. And I will be able to show you some of this and some of the more advanced examples. But anyway, just suffice it to say that this is I would say 90% of getting them to work correctly. And we'll see that further on. But for right now, the test set is just as critical as the training set. So first you want to select the data points between training points to test the ability of the neural network to interpolate. You also want to select data points outside of the training set regime to test the ability of the neural network to extrapolate beyond its learned mapping function. So you can see here the blue points are the actual training data, and I've set them up like this, as you can see, and they stop right here. The test points are red, and you can see them kind of interspersed between the training points, and then they go beyond, quite a bit beyond the training points. And so we'll find out whether the neural network is able to extrapolate and how far. But this is an example of where you can visually look at what your training points look like and then what your test points look like. And you'll get experience with this as far as how to set them and what makes sense. Okay, this is sort of the same thing, but kind of looking at the actual data. So here's the original plot that we were looking at, and this is the actual training set data itself. Xtrain is the array of X inputs for the training set. So this would be all the blue points that you see here, -12 to +12. And then Ytrain is the Y array of data, the Y output. So for example, for -12, you're going to get an output of 144. For -9, an output of 81. This is the Y equals X squared function, of course. And then the test set goes out to -16, which is right here. And then its output, or the Y value, is 256. And you go to -15, the value would be 225, and here you can see that, and so on. So this just gives you an idea of what the data sets would actually look like. You have and this is what we're going to work with. This is your training input set, training output set, your test input set, and your test output set. Of course, this data will all be scaled, but this is the foundation of what you're going to be training the neural network on. Alright, so we've moved on to the next step, which is to scale the training and test data. In order to understand this, you need to understand what you're actually working with. Why are you scaling the data? Well, you're scaling it because it needs to be able to be processed by the processing function, or they also call it activation function, which in this case is simulated by a hyperbolic tangent function. And this is what the hyperbolic tangent function looks like. When you input these values down here over the x-axis, these are the y values that you get. And one of the things with the hyperbolic tangent is that you have this nonlinear curve, and that's part of what makes the neural network very effective. But it's important that you scale your input data and your output data appropriately. So for example, for inputs, you want to keep your data roughly in this range. If you come way out here where this curve asymptotically approaches -1, which means it never gets there, your data is not going to vary, because it's just, this curve doesn't change. So you want your data where it varies all the way from here, in this case -0.9, all the way up to +0.9. So you want to be able to have changes, negative and positive, in the output. You don't want your data way out here. You don't want it way out here either. Now, this is what we call the nonlinear region, which is the blue square, where you can see the curve change nonlinearly. And then this little red square is sort of the area where it's just the curve is basically linear. And so for some applications, you can have the data in there, or you can have the data constrained to be within this range. In other cases, it's better to go out as far as possible in the nonlinear range, which helps the neural network do a more nonlinear mapping. So for input, for scaling your training and test data, you must keep in mind that all inputs should fall into an interval of approximately -1.5 to +1.5. So this is -1.5 gives you a value of -0.9 approximately, and +1.5 gives you a value of approximately 0.9. Now, I'm not saying that your data should always be scaled this way. All I'm saying is you really shouldn't go much further than that. If you want to scale -0.5 to +0.5, or 0.8, it's whatever works for you when you're experimenting. But just understand the effect of what the input scaling numbers are like. This creates an output interval of minus 0.9 to plus 0.9. So you get minus 1.5, as we said, is 0.9. 1.5 takes you to plus 0.9. If you go out much further, you're not buying much as far as increased delta input. The change, which means if you go out this way or that way, the change in y is very little. You're not going to have anything happen, so it doesn't do you any good to have your data out here. For some applications, it can be important to include the nonlinear curve as much as possible, and this is gained by experiments and empirical testing. So for the output, for scaling your training and test data, you must keep in mind that all output should fall into a maximum interval of approximately minus 0.9 and plus 0.9. So your output data, you would want to put somewhere here, because you don't want to let it to go off into this very sort of static, swampy region that doesn't do anything, and also minus 0.9. And again, you can make them smaller, but just don't go much further beyond that, or you're not going to get much movement as far as the ability of the data to change, or the neural network to come up with different solutions. So we're going to continue what we were looking at before with the scaling of the data, but explain how do we get that data scaled to where the activation function can handle it. So the easiest way to scale the data is to use linear scaling with the equation y equals mx plus b, where m is the slope and b is the intercept. Thus you're scaling the data to fit within a certain data interval that is acceptable to the neural network, well, very specifically the neuron or activation function. So for example, let's say the x data is minus 10 to plus 10, but you've decided your maximum and min values for the activation function are going to be minus 0.9 to plus 0.9. Well, you've got to get that data scaled down to that regime or that interval. The other thing is, in this particular application, the two data sets are not the same size. The actual training set is larger. So we need to do the scaling off the larger data set, because if we didn't, and we trained off the smaller, or scaled the smaller training set, then when you go to actually apply those scale factors to the larger data set, it would go out of bounds. So we're going to start with the training set, and we're looking at, in this case, we're scaling the input values. So we're going to start with the test data set for x, and we want to find the max and min bounds of the test data input. So that might be minus 16 to plus 16. And we want to bound it so that instead of minus 16 to plus 16, we want it to go from minus 0.9 to plus 0.9. So how do we do that? Well, we use this equation here to actually scale it. So we take the max and min of the actual raw data, and then what we want to set it to. So we calculate the slope, the intercept, and then we can, once we have computed both the slope and the intercept, we can now calculate what the neural network training input set is going to look like. So you would take the raw training input data, multiply it by the slope, and then add the intercept, and now all of these values will fall between minus 0.9 and plus 0.9. And then what you want to do is plot the data just to make sure, once you've done this, that it is what you think it is. In this case, the training data is in blue, and it falls between minus around 0.7 to plus 0.7, and the test data falls between minus 0.9 and plus 0.9, and that's what we wanted, that the maximum would be minus 0.9 to plus 0.9. Note these are the actual data set numbers, so this would be number 8 of the test data, number 8 of the training data, and there's less training points obviously than there are actually test points. So again, you do this correctly, then this is what you should see. Something, you can check the bounds, say, okay, I'm good to go, now I'm going to go to the next step. Okay, we're now at the point where we want to determine the neural network architecture. As I have said previously, really the most important part of this effort is the data set. The training set and the test set is really the 90% of it, but the architecture is still important, and we start off with the basics. We have one input and one output. Since there's one input and one output for this function, the neural network will also have one input and one output as shown. Note that this is just an example of particular neural network architecture. In this case, there are 2 hidden layers with 2 neurons in each layer for this example. However, you can experiment, try other combinations of hidden layers and neurons per layer. And always keep in mind the intent for this neural network is to learn this nonlinear function. Always keep that in mind as you're going through this. One thing to remember though is if you're having problems, it's not mapping very well, not learning very well, and you keep experimenting with more hidden layers, more neurons, and it's not working, I can tell you right now, 99% of the time, it's because there's something wrong with your data. So instead of spending a lot of time with the neural network architecture, spend most of your time on your data, understand it, and if you do, and you understand what behavior, what patterns you're presenting to the neural network, everything else will fall into place. And finally, we're at the point where we're going to train the neural network. So what does the train the neural network mean? Well, what it means is you want to set all of these gains such that every time you put in X, you're going to get the value of Y that you were looking for. So with the quadratic function, if you have a value of minus 10 and you want to get 100, then when you put in minus 10 or the scale value of it, then you'll get the scale value of 100 out here. And this should work not only for the training points but also the test points as well. So the objective is to find values for the gains G1 through G8 such that for each input value of X, the neural network will output the correct value of Y. And as I said before, this is both obviously for the training case as well as the test data. So algorithms for determining the gain values include backpropagation, which is very, very old, Levenberg-Marquardt optimization, and there's other methods. I've always used the Levenberg-Marquardt optimization. It is extremely fast and has worked across all types of applications, but you can pick whichever one you like. As I said in this tutorial, we will use the Levenberg-Marquardt optimization algorithm because it's very fast. So now we are at the final stage. We've trained the neural network, and now we're going to test the trained neural network. So to test the neural network, you will feed it the test data inputs and compare the neural network outputs to the test data outputs. So in this plot, the test data points are represented by red circles, and the neural network outputs are represented by red stars. So here you have the training data, which is in blue. So again, you can see what we originally trained on. The circles are the test data. That's what the neural network should actually be outputting. And the stars are the actual neural network output. So in this case, it did pretty darn well. You got to consider these are all the points that it would have interpolated in between the training points. And this is all extrapolation going outside the training regime here. And it did remarkably well. Thus you can see how well or not the neural network was able to interpolate, that is, to produce the correct output between training points, and extrapolate, which is produce the correct output outside of the training regime. If the results are mediocre, then the next step is to train another neural network and test it against the test data set. In reality, the software for this tutorial actually trains and tests multiple neural networks. At the end, it displays the results for the best performing neural network. And that's typically how I do all applications. I run multiple neural networks and look for the best performing one. And again, using the Levenberg-Marquardt optimization algorithm, generating neural networks is nothing. Usually takes either a fraction of a second, well, I wouldn't say a fraction of a second, a few seconds, but it doesn't take long to actually produce them. And so again, for this particular case, the neural network did quite well, interpolating in between the training points and then also extrapolating outside. So this concludes this tutorial.